Hello and welcome back to Calculus 3, to the shortest section of all. It is. Do it. Turn-wise. Done. Vector valued function is going to have three functions inside, right? If you need to take limit, take three individual Calc1 limits. If you need to take the derivative, take individual. Let's do an example, right? So, this is all we need to know. Do calculus term-wise. Each one of the functions within a vector will have its own whatever calculus procedure you are doing. Limit, derivative, or integral. So, for r of t equal, let's say, let's call f of t, g of t, h of t. You can go with x, y, z, whatever. Then, what is the limit as t goes to, I'll just put a, could be 0, could be number, could be infinity, of r of t? Well, it's just going to be limit of f, limit of g, and limit of h. As I said, term-wise, all of these are individual. All of these are individual limits. If you need to find r prime of t, which is the derivative, that will just be f prime of t, g prime of t, h prime of t. And if you need to integrate r of t dt, it will be integral of f dt, integral of g dt, and integral of h. Integral of h of t dt. Oh, I forgot plus c as a vector. Make sure you have this plus c as a vector at the end. It's not there for decoration. We need that. So now, our next lecture for tomorrow is motion in space. And I really don't want to now use the example where I say, here is the position vector r of t. What's velocity, what's acceleration? Because you just take derivatives. If I give you velocity vector, you integrate to go back, right? So all of those features from Calculus 1 still hold. If you are able to take basic limits, if you are able to take derivatives, if you're able to do integrals, this section is over, right? You already know how to do all of these concepts. Now, I do want to talk about two things in particular. One is the tangent line to the space curve, and the other one is this plus c for integration. So those are the two things that I want to specifically talk about in this one. The next section for tomorrow, 14.3, motion in space, is this on the applied example of motion. So first off, let's talk about this idea of the tangent line to the space curve. So you have your coordinate system, 3D, right? X, Y, Z. We are using the right hand coordinate system. And we have some kind of a flight pattern over there of a bug. Let's curve it more. There we go. And you are looking for the tangent line. Let's do different color. You are looking for the tangent line right there. So TL. TL, tangent line. The red line here is given by R, right, of t, which is your f of t, g of t, or x, y, z, whatever you want, h of t. So the red line is given by that. But if you recall, tangent line, let's put this, tangent line is a line. And the line has equation x equal x0 plus at, y equal y0 plus bt, z equals z0 plus ct. So tangent line must have this form. Please don't hand on the exam answers to the tangent line with x squares and 1 over x's and things like that. It has to be linear line. So we understand that this ABC vector, we call that vector v, is, I'll put in quotes, some kind of 3D slope. That vector is the vector in the third-dimensional space which curves, right? Which shows the direction of the tangent line. So this TL has slope m as v, vector v, right? Slope m, let's put this 3D slope equals vector v. Now we know how to find slopes, right? We take the derivative. So you should be able to take the derivative of the curve and then just come up with it. So vector v, which is the ABC, will be f prime of t, f prime of t, g prime of t, and h prime of t. These are basic derivatives. Compute at the point, and that point is going to be x0, y0, z0, which the point came in from t equals to some value. So let's take a look at example. Find tangent line to the curve r of t, let's say t squared plus 3, 1 over t, e to the 2t, at the point 1, 1, 0. So find the tangent line to the space curve. Well, first you have to come up with that third-dimensional slope. So you need your r prime, which would be v, which is your ABC, right? So that's going to be 2t, negative 1 over t squared, and 2e to the 2t, when you take independent derivatives of each one. So you took the derivative in respect to t for each one, and now vector v is going to be 2, negative 1, 2. What I calculated here is, so plug in 1, 1, 0, right? And I have my vector v. Now I need my x0, y0, z0. Which is when I plug in the point. No, sorry, x0, y0 is actually equal to 1, 1, 0. There we go. That's already given to us. And now I can just put the tangent line together. I can put tangent line together, which is x equals x0, that's 1, plus 2t. Y equals y0, that's 1, right? That's the y0 right there. Y0, and then minus t. And the z is equal to 0, 0, 0, all zeros, so just big fat 0. There we go. That's the tangent line. So in this problem, you were given location in space and you calculated. You don't have to be given location in space. You can just be given time. So let's say find tangent line at t equals to 2 for r of t equals to t cubed negative t and I don't know, 4t, whatever, it doesn't matter. Come up with anything. Your vector v is going to be the derivatives 3t squared negative 1 4, which when you plug in t equals to 2 you get vector that it's 12 negative 1 4. So that's the slope, the 3D slope I was talking about. Oh, come on. There we go. And now if you want, and you need the point, the x0, y0, z0, well, that's going to be your original function r, because you're looking for a point on that line. So you have 2 cubed is 8, negative 2, and positive 8. So x, y, z. The point is 8, negative 2, 8. And the slopes are 12, negative 1, and 4. So plus 12t, negative t, plus 4t. And this gives us the tangent line, the three tangent line. So you can be given a point, right, to find the tangent line at, or you can be given the time, the parameter t equals 2. If the point is given, well, you're done. You don't have to compute the point because point is given to you. But if they give you the time, you have the function, you can plug that time into the function to come up for the point at which you are looking for a tangent line. And then the derivative of the space curve, which is this one, is this. Now, I did promise when I talked about the line that I will eventually tell you why they picked V to be the name for that. Did anyone connect the dots by now? Why was letter V picked to be the slope of that, of the a linear line when we learned it for the first time?
Would we
What happened?
would be like V for variable? Right?
Nope. Not V for variable. V for, okay, V for vendetta, but what else?
What about possible shape?
What?
So it's because the line represents a vector.
Nope. Wow. Vector is another thing. Okay, but no. But yeah, good.
It wouldn't be because of the possible line, like the structure of it. I don't know, just guessing.
You're just guessing it, but maybe you connected because I already said it once. Why V? Why not M? M is a slope. Why V? What is R representing? Function. And what is that function? What is that representing in the real world? Because right now we're in a fake world when we do math. What is the R in the real world? Position. Beautiful. Now, what is V equal to?
Velocity.
Velocity. Exactly. V is the derivative of R, right? R prime was equal to V. R prime, if R is a position, R prime is a velocity, and then that's why we use V. So that was actually, right, the naming for that vector to be V was well after, right, all of the vector valued functions and everything else, and say, okay, we can represent this, and then you go back and just label it as V. So VT, what is V? V is the velocity. Velocity is meters per second. T is time in seconds. When you cancel them, right, you get another length, because you can only have length plus length equals length. That's the best way to learn physics, through dimensional analysis. In our problem, we had that R was equal to R0 plus VT. This was what we had. So if we said that R was distance, so that's in meters, R0 location distance, again in meters, velocity, meters per second times second, when you cancel them, meters plus meters gives you meters. In physics, units always have to work out that way, otherwise equation is garbage. All right, so that was the tangent line. I did 2 problems instead of 1, such is life. The second part is plus C for integration. This is a terrible title, but if I don't talk about it, then the whole types of horrors emerge at the exam, and then I just get annoyed. So, first of all, we understand that the plus C for integrals is not optional, and it's not there for decoration. Derivatives destroy constants. Derivative of 10 is 0, derivative of 1,000,000 is 0, derivative of -5 is 0. So, being that integrals are anti-derivatives, they undo derivatives, there is no way to resurrect the constant that was deleted by derivatives. So if you have the derivative of x squared plus 6 to equal 2x, and you do integral of 2x dx, well, you get x squared. But you don't get this plus 6 back. So we go with the plus C as a placeholder because we don't know what was there together with x squared. Maybe it was plus 6, maybe it was plus 10, right? We don't know. So we just put that plus C there as a placeholder, saying that there might have been some constant. Now in that case, this means that the answers that you get here are infinitely many parabolas all stuck on top of each other like this forever and ever and ever and ever and ever, because any single plus C that you can come up in your head will give you one, and exactly one of these lines. So that gives a rise to a problem which we call initial value problem, where if you provide me with a point in space, I can calculate C. So if I am given, well, now a new problem. So integrate, let's say 2x cubed minus 6, right? Integrate that. And have the function go through, and then you just come up with whatever point you want. -1, 19. It doesn't matter. Nice one. So what do? You integrate, which is 2x cubed minus 6 dx, and that is going to give you 2x to the 4 over 4 minus 6x plus c. That will be 1/2 of x to the 4th minus 6x plus c. So this is what we call indefinite integral. But now, this is actually a function. We call this capital F, antiderivative. And you can use negative 119 to calculate value c. So now you can say that the capital F of x is equal to 1/2 x to the 4 minus 6x plus c. And you calculate, so f of x, that's the y, so that's 19. And then you have 1/2. Over here you have negative 1 to the 4th minus 6 times negative 1. So this is 19 equals to 1/2 plus 6. And c is equal to 19 minus 6.5. And that is 12.5. So we calculate the value of c. But in order for you to calculate value c, you have to have the value given. So now, if you translate this into the 3D realm, you just have to do 3 of these problems at the same time. Because if you have to integrate your r of t dt, you will get the integral of f dt, comma, integral of g dt, comma, integral of h dt. And when you integrate each one of these, every single one is going to spit out its own plus c. So plus c1, plus c2, plus c3. So we have, nice one, we have capital F of t plus c1, then capital G of t, these are all antiderivatives, plus c2, and then capital H of t plus c3. Technically, you can just put this as f of t plus g of t plus h of t plus big fat vector c vector, which is the c1, c2, c3. Now, we are not learning any new math. This is just 3 Calculus 1 problems, all stuffed into a single problem. So the procedure you've seen up there to solve for 12.5, you will have to do for f separately from g, separately from h, and then you are going to get 3 different constants. You put them in a single vector, and you have the value. Now, clearly, when you are dealing with integration in calculus, you are just hoping to see particularly 2 functions, right? You want to see as much as possible of e to the x, because that's the cheapest integration. And hopefully you want to see just sines and cosines, because they just flip back and forth between sine and cosine. Right? So if you see those functions, then you should be a happy camper. Anything else other than that might be annoying to calculate the integral, or annoying to compute, or whatever, these simple values, right? So you want that. And that's it. So the next section is going to be, again, this stuff, except we are going to call r of t, we're going to call that s of t for position, and then v of t and a of t, and then we're just going to do a whole bunch of derivatives and integrals going back and forth. So let's go to the lab. Bye.